Dr. Ana Paulino Afonso is a junior research scientist at IAU Porto in Portugal. She has a PhD in astronomy and astrophysics from the University of Lisbon and has over 35 peer reviewed articles, with six as the principal investigator. Her research focuses on the field of extragalactic astrophysics and observational cosmology. Specifically, she works on studying the structural evolution of star forming galaxies across different time, epochs, and environments. She has worked on studying active galactic nuclei galaxy hosts as part of the GIA mission. Thank you. So let's talk about your personal background and career. How did you get interested in the field of astronomy, specifically galaxies?
So I was very, very young. I was like 8 or 9 years old. And I was watching television. And the Hubble Space Telescope was giving new views of the ultra deep universe. And there were new simulations on our own galaxy. So about our arms and the number of our arms and bars. So and it was like puzzling to me. So I do remember being in front of the television, a little bit puzzled with all the information that they are showing in the news. So I think it was on that moment that I realized that I want to understand more why we are here and why, in particular, galaxies should matter to have a
Yeah.
planet as ours. So basically, it was like that.
Yeah, I think that's every child's dream at one point. Because myself, I wanted to be an astronomer at one point as well. So, moving on to the next question, what would be your advice to people like us who want to be astronomers in the near future?
Well, so I think it's important to remember that we are living in a very amazing era. I'm not saying that that was not other amazing eras, but now we have this a lot of space telescopes. They are planning to have more telescopes in space, and they have these bigger telescopes also on Earth. So the amount of data is a large number. So you are in a in the right moment if you want to be an astronomer to explore the universe. So I think that it's important to be perseverant. So it's not difficult to become an astronomer, but it's difficult to stay somehow in the field. So to keep motivated. Okay, it's more than just study and know a lot of physics or mathematics or English or coding. It's more than that.
Hmm.
Okay, this is a good start. If you like to do questions and if you like to understand things, it is an amazing start because it will keep you motivated and you want to learn physics, mathematics, English, coding, um, and you are on the path. But then you have more. You have a difficult field to be. So all academia is difficult, not particular astronomy, because there are a lack of positions, there are a lot of competition, there are too many demandings. So it's sometimes I think it's hard to keep motivated. So I think it's important that okay, I have this question and I want to solve it or I want to understand it better, and this is what makes me feel in love with for this. So let's keep trying. So perseverance, I think, is everything nowadays.
So I think you have heard the quote, right? Necessity is the mother of inventions. So I think just like that, what I feel is that on the same lines, curiosity is the mother of scientists. Yeah.
Yeah, I think it's all burns because you want to understand something, right? So you are curious about something.
Yeah.
So why the sky is dark during the night? Why are this right? So this made us an humanity, right? So a society and the evolution of everything that we know, it's due to that basically. So
Yeah.
and we didn't understand everything. So curiosity is very, very important.
Okay. So moving on to your technical aspects of the work, you have worked a lot on galaxies and star formation and galactic evolution. So our community had some questions regarding that. So here's the first one. Galaxies are expected to form stars as efficiently because gas falls into them due to gravity, right? However, observations show that fewer stars, uh, like the prediction models show more stars than the actual reality. So this suggests that a mechanism is preventing gas from collapsing and cooling efficiently. What do you think that is?
So I think also the theory and the observations taught a lot of things in our life, right? So we have these amazing models to try to understand um, how things form and evolve. And the more basic explanation, and because you are trying always work on the more basic thing because it should work, but at the same time, we know that probably things are more complex. But
Yeah.
on large scales or first approach, gravity is everything, right? So gravity rules everything. So our models are just our first models are just based on gravity and how gravity should work. And if you only assume that, of course, we should have a lot of sublimation happening. But this is not the issue because, as everything in our life, things are more complex than that. Because if you have something forming, so you have imagined the first stars, like us, unfortunately, they born and die. So we need to think of this that part. So this supernova, basically, and how it may give feedback to the environment, right? So this is one of the things that we need to take into account, and we also need to take into account aging. So when you have an eccentric, a center of the galaxy that is active,
Mhm.
we also have feedback due to that. So we know that mainly due to these two processes, and they may have more or less feedback depending on the galaxy that we have, they diminish the number of stars that we are forming. So that's why they are not super efficient in forming stars because stars also died and they can die in a very aggressive ways or violence. And we can also have active galactic nuclei playing a role. So it might impact a lot
Okay.
how many gas and how many cooling, how coolest can be the gas to form stars. This is the main thing that is happening.
Okay. So I also was going through some research papers of yours, and I also saw this line which really interested me. It basically mentioned that higher metallicity environments, basically places with more metals, lead to enhanced star formation rates. Why is that?
So one thing is important to know that in astronomy, and I know that is not like in chemistry or geology and other fields, everything that's metal, so it's everything above helium. So only hydrogen and helium are like no metal things. Everything else is like metals for us.
Okay.
Sorry. And this is important. Why? Because these metals that we call, one are more metals than others, of course, they will help us to cool the process. So they will help us. If you have more metals, we have the opportunity to have a reflection of UV radiation that is happening in the field. We have the opportunity to start having dust grains. We have the opportunity to cool the system. So, and all of these will help to form the ideal conditions to have star formation. So if you have more metals, we have more conditions to increase the star formation because it helps us in particular in the cooling process. So
Okay.
basically it's what happened.
Okay. So talking about cool and hot, we also your papers also talk about halos, right? So first of all, could you like elaborate on what a halo specifically is?
So you are talking about the halo of the gaseous halo that we have around galaxies, right? So and you can have so basically the galaxy is not just the little points that you see that you can be in stars clusters or not and the galactic center we have a lot of things, right? So the galaxy is a combination of stars, dust, gas, when possible or most likely an agent as well, dark matter, and everything else you can think in the between. So everything that is connected gravitationally to the n element, basically. So the number of stars and the AGN, of course, impacts a lot for what we call the mass and of the galaxy, and to do the galaxy as the dark matter as well. But we have a lot of other gas around the galaxy, and this galaxy could be cool or hot.
Okay.
And depending the process that we have happening, we can have these hot gases halos that we have around the galaxies, um, and these basically what they are powered by a lot of process, but mainly by AGN activity. But what happened basically is that they are not helping us to do the cooling. So you know that cooling is very important in the past form star formation. Now we have this due to a lot of process, depending if you have interactions, if you have, for example, in a cluster of galaxies, you start to have this halo that is so hot. So we start to have more pressure on the galaxy. We start to not have enough power of cooling. So we are killing the star formation. We have a lot of feedback, and you have, if you are in clusters, and mostly happen in clusters, you are have interactions, and these interactions are stripping away the gas that you have to form galaxies. So it will starting quenching the galaxy, killing the galaxy. So basically, what this is halo is about, and what is the process that can starting have that. So,
Okay.
so starting hitting the galaxy and killing it, basically.
So I think that's why hot halos cannot form galaxies because they'll just kill the galaxy instantly.
Yeah, cannot form stars,
Yeah.
because you still have the galaxy, but you have the relays of, so you are having the ending galaxy. Yeah.
Okay. Okay. Then now talking about more halos and moving on to dark matter halos. I had this. This is a personal question of mine. In the dark matter halos, is the matter's density constant?
No. So first of all, and this is I know that it is strange. We have these names about dark energy and dark matter, and a lot of things is dark in the universe, but mainly dark matter and dark energy. The term dark means that we really don't know what's going on there. So we can have theories, of course.
Okay.
We have a reasoning why you need these dark things, but we don't really know them as of now.
Okay.
Okay, so it's very hard to say, oh, okay, this is like this or like that, because to be super honest, no one knows. So what we do is, from what we can infer and why do you need to have them, and we know that we need it because when you look to a galaxy, we see that the orbits of the stars, given a certain radius, is starting to become constant, and it shouldn't happen by the Newton's gravity, because you know that near to the center it's be
Yeah.
super fast, but then it's slowing down, but it's at the same rate, not becoming flat. So you know that. Um, so you need this dark component to understand what's going on. And we try to do a lot of ideas, to equations, simulations, and so on, to try to understand what best fits to it. And our best understanding as of now is that no, it's not constant. So a constant profile, not clearly explain everything, all the elements that we need to put this dark matter. We will need a model where the density in the center is higher than in periphery, so it is decreasing with the distance. And this is the typical model that we have. But of course, more models exist, and there are a lot of discussion. It's not something, so it's not created in the stone that should be like this. But our first approach, or our best models as of now, we assume no, that is not constant, and it is super high in the center and decrease to the periphery. And basically what we the model that we use is Navarro-Frank-White model that
Mm-hmm.
fully describe this model.
Okay.
But things might change. Okay, so now with
Okay.
Euclid in space, and in March 2025, we'll have the first data. It's not cosmological data as of now, but in 2026, we'll have the first cosmological data. And who knows if someone appears and say, okay, this is not fully correct, and we
Mm-hmm.
need to revise it, and maybe it can become constant. But as of now, we think that is not.
Okay. So breakthroughs incoming.
Yeah.
Okay, so how do these dark matter halos affect the shape and size of galaxies?
Yeah, so gravity is planing, right? Basically, what we think is that gravity is planing. So bigger halos, bigger galaxies, more potential to have um, more stars, but more feedback and more AGN, more interaction. So pushing other galaxies and become bigger. So it shapes the size, the color, the state of the galaxy. So everything changed. So yeah, in generic terms, they affect the shape and the size of the galaxies. And mainly is like what we know about the baryonic matter. So basically, one all in plane with gravitational pull. If you have more if you have more force to push attract things, and you have more potential to attract things, we'll have
Yeah.
higher, bigger galaxies, and all that it comes. So more interactions, more different shapes, um,
Okay.
whatever you can think, basically. Then it depends on the large scale structure and so on, how many interactions you have, and it's more complicated. But um, yeah, of course it plays a key role on shaping the evolution and the size of the galaxy that we see today.
Okay. So you mentioned how dark matter is different from baryonic matter, right? Now, more on that, could you explain the discrepancy between the amount of baryonic matter detected shortly after the Big Bang and the amount of baryon matter in more recent epochs? Why is there a difference?
So we don't have this is the answer yet. It's one of the big problems. But you are talking about the missing baryons, right? So from the cosmic microwave, you can infer the amount of periodic matter that we have, and now we have today's observations. And if we count all the photons, you see that they don't match. And we have a lot of ideas for what might happen. We think that most of these missing baryons may live in the intergalactic medium, and they are spared, so it's difficult to go there and
Yeah.
pinpoint where they are and really connect. So they are not, in the sense that they are not connected with the galaxy or object that we can really count the flux
Okay.
there and help us to understand that. But probably it's not everything. Like I said in the beginning, we normally have like this first approach, but reality is always more complex than this first approach. So we might have a problem with the temperature as well. So they are very high temperature baryons that we need to catch with X-ray and ultraviolet, and even so, it can be very very hard to catch them. So we might be missing them due to that. So better observations are needed. Um, we can have still lacking on the observation part to get all this information. Um, we can have even our structures, what we call the cosmic web, our fingers and so on, but we have like missing small substructures of these, and we are really missing the point. But I have more ideas on that. So 1 month ago, more or less, Euclid launched his early release papers on for science. Um, and one of these papers is very, very impressive. So they target a cluster. where they already knew some dwarf galaxies, so small galaxies that we have. And in that cluster, we had an idea about 500 galaxies. But with Euclid, and Euclid in a couple of hours, not much time, okay?
Okay.
We discover more, so it doubled the number. So we have like more than 1,000. So it's 500 more these dwarf galaxies. So problem is missing baryons. It's a lack of our observations in the multiple sense. So not only these baryonic elements that are disconnected and lost in the intergalactic medium are only visible due to high temperatures in X-rays or ultraviolet, but they are also galaxies that we didn't discover. So maybe we need better eyes and more time to see them, properly see them, to really compute the baryonic fractions and to properly compare with CMB. So there are theories, but I think behind the theories, we are missing more observations and a more clear understanding of our universe. And it's normal that we don't have it, okay? So it takes time. So there are, I think that is this observational effect, plus these normal things that can happen. So cosmic web is complex, things may not groupy, it's okay. Temperature play a role, so a combination of effects that doesn't allow us to properly see them. Or we're still missing that in somehow. We need the new physics and understanding of universe, and he's also cool.
More breakthroughs incoming. Okay, so moving on to the observation part of this, like you mentioned, how do astronomers right now measure the density and the mass or the volume of the baryons that are present in the universe right now?
So one important thing to note is that no one goes there and really count them, okay? So it's not possible. So what you need to think of is how we should try to count things with information that we have. And the most simple way is, okay, we have our eyes that are powered and magnified by our telescopes, of course, and try to think what are you looking at. So you are looking at galaxies. The light that we see is mainly due to stars, right? So that's what's shining. So we compare this with our own star, our sun, for which we have our nearby stars that we can use in as a model. So we just compute due to that, right? What is the best combination of stars that can reproduce that light? And having an idea of the number, so we can count the number of photons that touch our telescope, right? Of course, it's not all of them because we always have a loss, but the ones that we can count, we try to see, okay, this number is mainly due to stars. This is the best templates I have for stars, assuming that the stars are similar to the ones in our galaxy and the ones that we know, of course, and also the sun, that's the one that we know better. We have these templates and just try to combine templates and try to reproduce a number of flux of photons that you are receiving in our telescope. And with that, we can have an estimation, the stellar mass, and of course the number of stars, basically, and also the metallicity of the galaxy, star formation rates. So this main information comes to that. But this is only in the optical and near infrared, okay? So, and this is the more basic way to understand. Then we didn't bore. So then for the gas, for example, we need to go to the radio. So at the 21 centimeters line, it's very important to understand this neutral energy and try to understand the quantity of gas that we have available. And also in the submillimetric domain, we have the CO, and we can also trace the amount of carbon monoxide that we have. So we need to also complement the gas that we have with the stellar populations that we have. Okay. But then we have cooler things, and or not so cooler, but then we have other things.
Yeah.
So we need to go to the X-ray and UV to try to understand this art process as well. And here we also have the hot gas, but also some information about the agent and its properties. And then due to the dynamics and some empirical evidence, you can try to infer the mass of the supermassive black hole and things like that.
Okay.
And then we also need the all process of intergalactic medium and how the number of clouds that we have there.
Yeah.
So we need to combine all of these to have an idea. Uh, and then we need to, so from here you need you have an idea of the number of stars and number of gas that we have available basically, but then we need to understand how it is distributed. So you need to like redshifts and large scale structures to understand. So it's grouping things and try to understand what is the volume that you are targeting and associate number counts to volume to try to infer all the properties. And then you combine all of these and you starting have an idea how things work and evolve since today until to the past, basically. So when you try to have to associate things, but basically that. So you try to be a child in the end. So in the sense that you are trying to group things and try to match what you know and try to infer the basic properties. And
Yeah.
probably we are missing stuff, but basically it's like that.
I can see why you mentioned initially that astronomy is more than coding, maths, and chemistry. Okay. So you mentioned IGM, right? Intergalactic Medium. So why does it absorb only certain parts of the electromagnetic spectra? Why not all of them or none of
So
them?
because it's more sensitive to some wavelength, right? So the size of
Yeah.
your emission is important, right? It's like you see it through the glass, to the windows. It's because radiation can travel and can pass. That's why you cannot see radio information, for example, right? And also your eyes are in the nanometer, so it's what you can really see. So something similar to what happened in our windows or our microwaves and so on is happening to the gas that we have in the universe. So if your wavelength is very short, it's starting to be trapped by the system, so it cannot allow. So what you can see is basically, so the information that you're starting having is how it will be captured by the system. So and it gives you the information about that. And there are other information that because they have bigger wavelengths, it can easily travel without any problem. But so shorter, more probability to be caught by the dust and liquid clouds that you have during the system because it's more interacting with them. So it's more or less in the same wavelength working. So that's why what is happening.
And how does the IGM or the intergalactic medium differ from the interstellar medium within the galaxies? Like, what's the difference?
So one is the location, right? So interstellar medium is between stars within the galaxy, and IGM is intergalactic medium outside.
Yeah.
So it's not the stars. So the location is different. So not the process, but the properties are somehow different because if you are targeting interstellar things, you are basically seeing the properties of the cloud that give origin to that stars and that's dominant by that region. Or imagine that a supernova that occur nearby. So the impact in the local environments. When you are seeing the intergalactic medium, you are seeing something that refers to the galaxies, basically, or the galaxy, basically. So you are seeing more all the feedback or all the situation that contribute for the history of that galaxy. So basically, it's two different things. So it's the location and what is probing. One is more the story of the galaxy. What is a particular region inside the galaxies?
Okay.
So they can be the same thing, but can now at the same time be super different because it depends of the history and the moment in time that we're talking about that galaxy. Probably, if you are looking for the ICM and IGM, when the galaxy is like 100 million years, it was probably super similar.
Yeah.
But today, no, that is not completely different history. Okay, so and it's because you are talking literally about different stuff, different things.
Okay. Okay, so getting back to my favorite baryons, and so could you explain what the Lyman alpha forest is and how it helps infer the mass of diffuse baryonic gas?
So Lyman alpha is the most basic uh, line that we have in the universe. So is the decay from the level 2 to the ground state. Basically, is the most basic one in the hydrogen line, the most fundamental. Um, but it's also a complex thing to catch because it's resonant, because it's get trapped by the dust, and also for molecular clouds and so on. So basically, what's happening is hydrogen is most abundant element in the universe. So it's normal that we have this kind of information, and it's common. So basically, what is happening is that these photons are being trapped by the system. So they are like giving us some hints of the information that we have between us and the element, in this particular case, quasars or hot or distant galaxies that we have. So what is the amount of neutral hydrogen that we have? So because it will be trapped, if you have a bigger cloud, so we'll have a very damped system because it will be very large and damped. If you only have patchy or very small clouds, so you have a smaller peak. So this Lyman forest will, the intensity of the forest and how deeper and how narrow or not narrow, broader it is, will give us fundamental information about the amount of hydrogen that we have between us and the source. So this is a way that we have to trace information and the available gas that we have to study these galaxies and try to understand. So this is what's happening with this forest system.
Okay, so talking more about observational techniques and baryonic matter, what is the Sunyaev-Zeldovic effect, and how does it provide insights into baryonic matter?
So the sun and dolphins, even me are having problems to say the name. The SDA effect. So I think it's better like this. It's an effect that the cosmic background radiation is distorted when it passes to the cluster of a galaxies. So first, cluster of a galaxy is a group of galaxies. Okay, it's like grouping galaxies in a system. And the cosmic microwave background is the first information basically that we have from the universe. So it's when the universe becomes transparent, so you can see it. It's the first things that we can see it. And it's uniform and homogeneous in the sky, more or less. So broadly speaking, yes. In detail, it's not properly like that. So the Sunyaev-Zeldovic effect is when you are seeing to a cluster, you see a distortion of the cosmic microwave background, and it because this information interacts with the system. Okay, that is very hot, has high temperatures because of the interaction of galaxies, the pressure, and so on. So the electrons. So the photons interact with the high energy electrons, and it's becoming distorting the signal. So, and this is very important to us to understand the clusters themselves. Okay, so because we'll have a thermal effect and a kinematic effect, and this can shape us in understanding how the system, so the large scale structure, um, evolved, and how we can use it to probe dark matter and also dark energy. So basically, what you'll try to see is that, okay, these effects should happen in all of them, and in fact we know that it happened, but small difference will tell us the state of the nature of things, and um, will allow us to have a better understanding how these clusters properties may might differ between them, and the nature of dark matter and dark energy in the end. So
Yeah.
basically, so we have a signal. The signal is dispersal, and this is a thermal and a kinematic effect. And the difference. So if everything is in the place all the same time, so because we can look outside the cluster and see the signal, and it's only a basic signal, so you only measure the distortion, and it's everything okay, right? But if you are not the same between clusters, it was also giving you some hints how the structures evolve, and very very small difference can give us a lot of information about these dark components and also the physics behind it. So you try to measure these properties and help on this way. So I know it's not very super clear, but I think it's the idea is that there is a signal that is distorted.
So after observation, the next part of astronomy is, I think, kind of understanding the data or interpretation. So can AI assist in automating telescope observations and making sense of the data?
Yes, so artificial intelligence is a very not new thing, but a hot topic now, right? And yes, we already use it alone in a lot in astronomy, and it is a reality. It's automatic. Put telescope doing observations, and also having a sense of what kind of observations should the astronomers look at or not. So I would say that, yeah, depending on what you want to do, it can make sense. What I'm trying to say is like, okay, we know that AI, it's good to make to allow us to be more free in certain terms to the repetitive word, right? So it's not changing us for the Ford model or things like that. Um, and we know that in all jobs, including astronomy, there are a lot of things that are repetitive. So if you go to the telescope, imagine that you are looking for supernova. Supernova source is one of the good examples, I think. So you know that you don't know where the supernova will occur, right? So there is no one is telling you saying, "Oh, I will explode today." So one knows. So you need to monitor the sky, and you need to look to a bunch of images from the past days and today's observation, and you need to compare to see if you have a spot where you have an increase of bright, and you need to see if if it is might be an artifact of the telescope or other object in the sky that can hurt the image or not. So you have this, you see that to do this every night for 1,000 of images in all telescopes in the world. So it's hard, right? So it's not impossible because people have done this, but you can find what 2-3 supernova per day, maximum 5, I don't know, and we'll need a lot of purples. Imagine that you want even to check one or confirm one. You can imagine the number of people that you need to do that. So if you say that, okay, I will program my telescope to run the sky in this direction, so take these parameters. If you have the good conditions, I can observe, take the images, try to do these steps to do a basic reduction of the image, and then compare with my historic of images and try to subtract and see. And if I have like this difference, okay, I can infer like more things that I can say, and I can say this to astronomers, and with that experience, they say this is a supernova or not. So
Okay.
you increase the number of people looking because they have to spend less time, and you can find like more supernova per day probably.
Hmm.
So this is one of
Yeah.
the things that make a lot of sense, and people are doing that, and even trying to remove the maximum possible false negatives. I false neg I sorry false positives, to
Okay.
have a more clear idea, and to give to astronomers, and to make them really work on the data, and uh, not spend, because you need to spend at the same time, but be more efficient in the way that they're finding, for example, supernova. But who calls
Okay.
a supernova? You can tell about gamma reverse, or space weather, or even to track near Earth asteroids, or other objects. So AI could be a really a help. But you have more. You can imagine that as of now,
Mhm.
the number of images that you capture by our missions or telescopes, they are not completely not measurable, because okay, we
Okay.
have Gaia is starting being a little bit of problem, but the others, okay, it takes several years to do proper analysis, but it's somehow possible. Okay, with a
Okay.
laptop it's possible,
Okay.
but with Euclid, LSST,
Hmm.
uh, W first, and many others that come in the way, it will be completely impossible. There is no laptop power. There is no people power enough to deal with all of the information. So if you don't make use of AI, um, you'll spend too much time to
Hmm.
organize everything, and little time to understand the data. So, and remember what I said, what we said, both of us, bring us to the beginning, is curiosity. It's why
Yeah.
this happened. So of course the middle processes are important, it's always important, but if you have more time to understand why and what's going on, it's
Mhm.
better for you, because you can do better questions. So I think AI appears in the right moment, or technology linked now, uh, uh, it will allow us to do great advances, and of course we are trying to maximize
Yeah.
as possible the use of
Okay. So life would be much more easier if SARS had a phone.
it. I think we'll have other problems as well, but yeah,
Yeah.
it will be easier in certain aspects.
Okay. So what challenges and ethical considerations do we have to consider before using AI in an astronomical landscape?
Okay, so I think I think it's a little bit generic. It's not only for astronomy, but
Okay.
your AI models, or everything that you use in AI, depends on your training data, right? So your training sample, it's how it will draw a model, and how your model will work. So there is no magic there, right? It's how you learn things. If your training data is biased in all ways that you can imagine, or if your quality of data is not well prepared, you'll have bias, you'll have problems. So you cannot draw conclusions. So I think that every field is not only astronomy, but every field needs to be concerned about it. So in particular in astronomy, the quality of data and the kind of bias that we can have in our data should be taken into considerations, and should be stately super clear to all that our models were drawn based on these, and there are these limitations. So, and if it works like that, that's okay. Okay, and we can always improve, of course, but we need to be aware where the data was trained and where it comes from, what are the particulars of the data, what kind of bias you may have, and what are the limitations of the models.
Okay.
Generically speaking, I think people are being being very serious about it, and have worked very nice on that, but it's important that we need everything, have this always in our mind. So avoid black boxes, try to understand what is going on, try to understand the interpretability of the model. So the models say that. So imagine that you are trying to find the most weird galaxy, and the model draws, says something that is weird. I think that is important that we try also to understand why it's weird, why the model is saying that it's weird. Okay, it can be really weird, but you also need to try to link with the physics, with the what is behind. And in that sense, I don't know if people are going happy to that, but it's important that we be interested on that, trying to understand really things. So curiosity again. Then model validation. So if you really can prove that our models are depending of the data, if they run in the other computer. So this is important to take into account. Also the computational resource and data storage requirement and management. I think these are all things that should be in our minds. Ethical terms. I think that most of the AI used for searching galaxies or searching supernova or to have the telescope working is not really direct with ethical in certain aspect, right? Okay. However, we have to be in mind to everything that we need to do to have things working. But we have more than that, right? We have the large language models that we can also use to help us to write or to help us to describe things. And I think AI is super important for make astronomy more reachable to others. For example, for impaired, visual impaired people, to try to show legends or descriptions of galaxy images is one of the things that we are trying to do. It's a super relevant one, but you need to be aware about our language, right? The models that we use behind, if they have bias when they are created. What are the limits? If you can use things to help, but what is the property intellect or not? So these kind of things also come to a discussion, and they are ethical questions, right? And also the scientific discovery, it remains to who when you use AI, because you have people that also help to develop the mobiles or made the things that AI to be used. So we starting to have a lot of questions. I think we don't have an answer. I think AI is not in the beginning, of course, and even all these of lunch are not in the beginning, and AI models have been used in astronomy at least since in the 90s. So sex structure is the most basic one to distinguish between star and a galaxy. And this is used by more than 30 years now. But I think we starting need to sit, to talk, to think to certain issues that are already an issue in other fields and might touch us as well. So there are very powerful things that we can do now that AI allows. That was, I'm not saying impossible, but more harder or implies more time to do. And in the way that put things more automatic, I think there is no ethical issues, but they come of a lot of other things that I think that may have ethical issues and we need to discuss them.
Yeah. Okay. So talking about technology, what do you think the future of astronomy would look like?
Bright. In all sense. So no. So we are having these amazing telescopes in space, right? So we had we have Hubble because it is already an amazing telescope, and we don't want that he never stops to work, or if it needs to stop, please, we need another one in with at least its capabilities or better than its capabilities. Uh, so, but we have James Webb, and I think everybody is completely amazed with what James Webb was able to achieve. And if everything's on works as planned, we'll have more 17 years of James Webb.
Mhm.
But we also have Euclid, and as I already said, Euclid is like an amazing um, survey of the sky. It's a 3D map of our place in the cosmos, and probably one of the things that we'll have uh, for decades, because nothing similar is planned for the next years. So, and this is a huge amount of data, and on top of it, we have WFORS that also huge number of data that will allow us to even go further than Euclid in certain aspects. But we have the extremely large telescopes on Earth. We'll have SKA around the Earth with antennas.
Mhm.
We'll have the continuous of course, Gemini, VLT, uh, and other instruments that we are planning to put, in particular, integral field spectroscopy. So it allows like the patches of the object to have a spectrum and image for each part. So the number of information is too many. And these what I said. So I think it will be bright because it's really bright because you are capturing a lot of photons and
Yeah.
will hit a lot of data.
Mhm.
So in that sense, it's also bright because you have data that you never had before to try to solve all the questions that you have, or even better, to create new ones. So I and now we are in an era that is more than light, right? So you have
Yeah.
gravitational waves, you have neutrino. You need to combine all this information between them, and you can because big data and AI has already mentioned. So I think it will be completely bright in diverse terms, but in particular to understand the origin of these dark components, right? To the dark matter and dark energy, but it's also for the other questions that you really have. That is another hurt, and if so, how it looks like. So I imagine that the next couple decades, I will say,
Okay.
and when I'm saying decades, I don't want to put people crying because oh, it will take decades. No, I think even in 2 3 years we starting having the first steps of these big telescopes and big data, and and I think we're starting having new ways to look for exoplanets, cosmology, even the origin of galaxies and their evolution. So I think it will be a dramatic change.
Hmm.
It will be a revolution, and it's happening. It's happening now. So I envision a platina. A platinum area for the astronomy, and very bright, full of data, where people can, and when everyone is welcome to work, um, and or to contribute in different ways. Um, and I see that will do change, or I hope to do
Yeah.
change.
Okay. So I have one final question, and this is kind of personal to me. So I wanted to be an astronomer as a child, but then my dad was not sure about it because astronomy, or at least cosmology, doesn't have a huge impact on the society, I think. Because learning about exoplanets, black holes, neutron stars, it's interesting, I agree. But does it really impact the common man? And that is my question to you.
So I don't think that anyone will be here,
Mhm.
and probably this is a very strong statement, but I will say like this: if cosmology was not relevant.
Mhm.
Okay, so if you think, right, um, of course the societies or the first societies already knew, and they are walking there around the world, but there is a moment where they sit, they stay, they grow, right? And what we know that is that they are fascinated by the sky,
Hmm.
right? So the bright lights that appear in the night, what are they? So cosmology is like the first science to be set. So saying that there is no big impact, or people don't realize it, is a little bit harsh, at least from my point of view, because probably most of things didn't happen in this way if we are not curiosity to understand what's going in space, right? So what's there, why it happens. So even all the laws of physics and mathematics that was created, and also the way that we think about economics and so on, come from these basic or more curious states of humanity.
Hmm.
So I do agree that um, it's easier to sell to a parent um, that be a fireman or an engineer will give you the knowledge or the recognition or the money that you need to be in your life. But in the end, you need to understand what's make you happy, right? And just because it's not super direct to life of someone. So I know that, for example, to be a doctor or to be a paramedic is easier. If someone needs you, you are there. You can save his life, right? Um, if you are an astronomer or a cosmologist, it's harder, right? Because you are not directly saving anyone's lives.
Hmm.
But the fact that you are thinking about um, that very bright spot very far away, or how this bright spot happening, just because of that, you are thinking about the way that the physics work or the technology needed to go there and try to explore it. And this is technology, this way of thinking, it's helpful to today's people lives.
Hmm.
So when you think about the cars and the security on cars, most of the things happen because people go to the moon. If they don't dare to go to the moon, they don't have to think about a thousand of things that we have today in our cars. And they are important to be safe and for our safety. So when we think about medicine, I know that it's hard to think about it, but even to go to the space and the way that you need to put astronauts in space and living in the space and the pressure and the draw and things like that, it helps us to have a lot of things, the medical equipment. Even the way that I look for galaxies, for example, the way that I have to interpret or don't have all the data or missing data and how I deal with that. It's helpful to, for example, to go and check your head. When people do a CT, they don't have all the angles, so they need the best algorithm to make a reconstruction to see that if you don't have an injury in your brain. So I know that people don't see this immediately or don't recognize you as the person that saves anyone's lives if you follow astronomy or cosmology. But if you are doing your things with love and really want to are curious and motivated, what you are doing in the end is very important because it keeps everything working and it can help to the new technology that will help definitely people's life. or in medicine, or to make more security, or to make more equity, or to make more accessible. So a lot of things are pushed because astronomy, because are people that are
Yeah.
looking for these dark components or bright components of the universe, they are not touchable. But because you need a skill set that needs to solve how to solve things without touching, without seeing, without missing a lot of missing information. So the way that you reconstruct all of these can be really, really important for today's life. So I'm a parent as well. However, my kids are very, very small.
Mhm.
And I know that it's hard to see. We want the best for our children, right? So we want them to prosper and have a perfect future without money problems or without health problems and so on. Um, and I understand that it's easier to see that a lot of professions are more easier to see that or recognize that. The others are more difficult.
Mm.
But I can assure you that uh, even you don't feel it every day, and because you won't feel it, and even if you are in a paramedic or a medical school and so on, probably don't feel it every day. But if you are dedicated and if you are really what you love, this field is very, very important to make um, this life in this planet
Mm.
more fair and more accessible to all and with better conditions. And just because people are looking for very far away things or not normal things doesn't mean they are making huge difference.
Mm.
And we know that. Okay?
Yeah.
And so if it's what you love, do it.
Mm.
Never give up.
Yeah.
And try to say to your parents with all the information is astronomy is allowed this, astronomy cosmology allowed this. And then a
Mm.
bunch of things, of applications of astronomy in our today life. So yeah,
Yeah.
I
That's
know
what
that
I will.
it's easier to say that I will find the next Earth. Okay, but then you find the next Earth, and okay, I think it's easier. It's difficult to say, ah, okay, I will find dark matter, and your parents or people will say, and your end could be like a change on physics, on particle
Mm.
physics. And particle physics is very important to solve oncology, for example, the cancer.
Yeah.
Who knows that you are not the future Nobel Prize due to that, right? So yeah, I know that it's difficult to see the today's application of astronomy, but they are a lot, and a lot of things are only achievable because some people decided to be not normal.
Mm. Yeah, I think passion is more important than money and everything else. So, yeah, I'm still pursuing a career in astronomy.
Yeah, if you do your what you have to do with passion, whatever job you pick, whatever, I really
Mm.
don't care. But if you do with love, it will be amazing.
Yeah.
Yeah, and
Okay.
it will definitely contribute to a better world. So I
Mm.
truly believe on that.
Okay. So I'll end the session on on that note.
Okay,
Thank
thank you very much.
thank you so much for being here today and answering my questions.
Welcome. Whatever you need, just drop me a message.
Thank you so much. This was really great, and I learned a lot. So yeah, I'll be making notes, and I'll rewatch the session. I'll make notes, and yeah.
Okay, thank you very much. And I'm so sorry for not being native in English. Sometimes it's hard to express myself. I'm so sorry for that. And for my cough, I'm having this cough for 2 months.
Oh.
I'm trying my best.
Mm.
And for the invitation, of course. And as I
Mm.
said, if you need something, if I can help, I will be happy to do it.
Thank you so much. I hope you get well soon.
Thank you. Thank you very much.
Okay, then I'll
So
stop.
have a nice night in India right now.
7:40.
I am so sorry for the hours, but this is
Oh, that's not. Yeah.
the one is that work for me. Thank you very much.
Thank you so much. I'll